Hi, I'm Russ Baker. We're going to look at linear systems again today, and we're going to solve the linear systems using something called matrix inverses. A couple definitions to start with. First of all, a square matrix is a matrix, as you might guess, that has the same number of rows and columns. If you have a square matrix, we can also identify something known as an identity matrix. And the identity matrix is a matrix in which all the entries are 0 except the diagonal, which consists only of 1s. That's the identity matrix. Once we have identified something called the identity matrix, we can say that two matrices are inverses of one another if they multiply together with a result of the inverse, the identity matrix. So here's a definition. An inverse matrix, A inverse, is an inverse of matrix A if and only if their product is the identity matrix. Now, one problem we have at first is to find the inverse of a matrix, or whether or not it even has an inverse. Let's look at a problem. Find the inverse of -6, 4, -3, 2, if indeed it exists. The test for existence for an inverse matrix is to find the determinant value of the matrix. So let's do that. -6, 4, -3, 2. The determinant value here is -6 times 2 is -12, and minus 4 times -3 is -12. That equals -12 plus 12, which is 0. That's exactly what cannot happen if we expect to find an inverse. If the determinant of a matrix, we'll call it matrix A, equals 0, then there is no inverse. So each time you're asked to find an inverse or use an inverse matrix, you should first check the determinant value to make sure that it is not 0. Let's consider next finding the inverse of a larger matrix. Here's a 3 by 3 matrix. We'll use our graphing calculator to go ahead and try to get this problem under control and see what happens. Let's go over to our graphing calculator. I've already entered the matrix into our system. I've put it in as matrix E. I'll take a look at it just to make sure. There it is. It's -1, -1, -1, 4, 5, 0, 0, 1, -3. If we want to find the inverse of this matrix, our first problem is to make sure it has one. We'll try to find the determinant value. Matrix, math, 1 of matrix E, which is 5, and the determinant value is -1. That tells us we know it does have an inverse, and so we'll consider finding out just what that inverse should be. With a graphing calculator, that can happen quite fast. We'll just go back and find matrix E again, and then we'll use the key underneath the math key, the X inverse key. We'll push that key and hit enter, and we find out that our inverse matrix not only exists, but it looks like this: 15, 4, -5, -12, -3, 4, -4, -1, 1. We could confirm that this is indeed the inverse by multiplying them together and getting the identity back again. Matrices can be used, in inverse matrices especially, to solve systems of equations. Here's how. If we let A represent the matrix of coefficients, that is, all the numbers in front of the variables. And B is the matrix of constants, that is, the matrix consisting of a column of constants from our equations. And we call X the matrix of variables, which is in fact the way our solution would be listed. We know that the product of the matrix of coefficients times the matrix of variables must equal the matrix of constants. We're going to take advantage of some algebra properties by multiplying both sides of this equation by the inverse of A, assuming that the matrix A of A has an inverse. Then we end up with the identity matrix, because the inverse times the original is the identity matrix. So we get identity matrix times X equals the inverse of A times B. But the identity matrix times X is just the X matrix again. Therefore, our solution to our system is found by simply multiplying the inverse of the matrix of coefficients times the matrix of constants. Thanks to our calculator, that can be a rather easy and quick operation to perform. Let's look at a system of equations and solve it using this new inverse matrix technique. Here's our equation system. X plus 3y minus 2z minus w equals 9. 4x plus y plus z plus 2w equals 2. Negative 3x minus y plus z minus w equals negative 5. X minus y minus 3z minus 2w equals 2. We have 1, 2, 3, 4 equations with 1, 2, 3, 4 unknowns. I've entered the coefficients matrix 1, 3, negative 2, negative 1, etc. into my graphing calculator, as well as the constants matrix 9, 2, negative 5, 2. Let's go over to the graphing calculator and see how we're doing. Clear this previous work out. Our first matrix I've entered in as matrix F. Let's take a look at it. There it is, 1, 3, negative 2, negative 1. Those are the coefficients of our first equation. 4, 1, 1, 2, negative 3, negative 1, 1, negative 1, 1, negative 1, negative 3, negative 2. Likewise, I've entered the matrix of constants in G7. Let's take a look at it. You can see that it's 9, 2, negative 5, 2. All I need to do to solve my system then is simply take matrix F, 6, inverse. Do not use your exponent key instead of this inverse key. It won't work. When you're using matrices, you may not use that exponent key that way. So F inverse times the G matrix will give us a matrix of our solution. There it is. We know now that X equals 0, Y equals 2, Z equals negative 2, and W equals 1. That's a great way to solve systems, isn't it? Now here's another use for systems, and we can show how matrix can solve a system and find the solution to this problem. We want to find a cubic polynomial, P of X, that passes through the points negative 1, 14, 1.5, 1.5, 2, negative 1, and 3, negative 18. We know that a cubic polynomial has the form P of X equals AX cubed plus BX squared plus CX plus D. Well, if we know 1, 2, 3, 4 points, we know the function value, P of X, and we know the X values, which we could substitute in there. Consequently, we can create a system of 4 equations and 4 unknowns, where the unknowns are now the A, B, C, and D. Let's begin to set up what that equation system would look like. First, we know that 14, notice I'm using this first point now, 14 equals A times -1 cubed plus B times -1 squared plus C times -1 plus D. That's one equation. My second equation would be 1.5, I'm using this one now, equals A times 1.5 cubed plus B times 1.5 squared plus C times 1.5 plus D. My third equation comes from here. -1 equals A times 2 cubed plus B times 2 squared plus C times 2 plus D. Finally, we get this last point, -18 equals A times 3 cubed plus B times 3 squared plus C times 3 plus D. That looks pretty complicated, but we can evaluate -1 cubed, squared, we can evaluate 1.5 cubed, and when we do that, we'll end up with a system of equations which can be put into a matrix form. I've gone ahead and done that for you, and this is what that looks like. Our first matrix, a matrix of coefficients, ends up looking like this: -1, 1, -1, and 1. Do you know why that whole column is ones? Do you remember why? It's because those are the D's, and they didn't get multiplied by any of the X values in this problem. The one that looks a little bit hard to take is this one here, but remember that was the 1.5 cubed, 1.5 squared. There it is, 1.5. And so we have this matrix. The Y values out of each of the 4 points were 14, 1.5, -1, and -18. What I'd like you to do now is stop the tape, enter these values into your calculator as matrices, and find the solution to the system. The solution to the system, remember, is the coefficients to a third-degree cubic equation. Do that now, turn off the tape, turn it back on when you're finished. How did you do? Let me show you the answer, and then we'll go ahead and do it on our calculator to show you that it really does come out to be that. Here we have it. We have that the X matrix turns out to be -2, 5, -4, 3. This is a long problem, but let's try to remember just what it is those numbers represent. They represent the coefficients of the variables in a cubic. So let's put them in. That means that the required cubic equation was -2x cubed plus 5x squared minus 4x plus 3. We can go ahead and do that on our calculator just to confirm that final solution as one last trip. We'll turn that off. We'll go to matrix. I have this matrix loaded all the way down in 8. Let's take a look at H. There's my matrix, -1, 1, -1, 3.375, 2.25, -1. Where are the other ones? Oh, well, you know, if your calculator can't get all that stuff on, it just scrolls over so you can see it from there. So the entire matrix is really there. You just may have to do some scrolling to find it. I hope that didn't cause you any trouble when you were doing it. Now let's see what my matrix I is. Not to be confused, of course, with the identity matrix. Let's see what it looks like. There it is, 14, 1.5, -1, and 18. Those are the constants. Now let's calculate the solution using those matrices, H and I. We'll go matrix H inverse times matrix I equals. And we see that we get the solution -2, 5, -4, 3, just as we expected. The use of inverse matrices to solve systems is a very powerful technique. You should practice it until you can do it without making errors of entries into your calculator. So practice this. The varied applications where you may use it will be amazing to you.